Hey, beautiful class. We're going to finish our second lecture in chapter 4, talking about cyclohexanes for most of this. Then we'll get a little bit into lipids and oxidation reduction. So one of the cool things about cyclohexanes is we can draw them differently. And this ends up being important when we talk about cis or trans conformation. So generally, if you have a cyclohexane, we draw it like that, and that looks flat, right? And that is not a good indication of exactly what a cyclohexane looks like. Instead, if they were all flat, there would be a lot of strain, right? So instead of looking like this, they actually take on this conformation where you have one up, one down, one up, one down, one up, one down, and they look like what we call like a chair. Like, I don't know, I'm not going to do this chair any justice, but like whoop, 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 whoop. Like if you were to go sit in a chair like that, like a reclining chair. Yeah, that's why I chose not to do art in college. Anyways, so it looks something like this. We call it a chair form. There's two different ways to draw a chair form. You can draw a chair form like this, and these are hard for me to draw for some reason. Or you can draw a chair form like this. So you're going to have to kind of get used to practicing. I think they kind of look like lightning bolts when I draw them. This is obviously much prettier, but you'll see soon enough that they are harder than they look. So just give it a try and make sure you can draw both of these structures. So one chair is this way, and actually the reason we drew this is because this way is because oftentimes these things flip. And there's two different conformations. There's one where we consider, like, if we consider this a number 1, this would be the second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. And in this case, what happens is it flips down. This number 1 goes down here, so that's 1. And this is 2, 3, 4, 5, 6. So this is two different ways to represent cyclohexane, and they're usually in equilibrium. And we'll talk about which one it would make more of, depending on the situation. Again, just kind of recognize that here, this one's pointed up, and when we flip it, this one comes down here. And then this one goes up there. That one comes down here, and then etc. Whatever was up over here will be down over there. All right, so let's talk about drawing chair conformations with hydrogens. So kind of the easiest form, the one you see the most is actually generally this one. I think it's because it's the easiest to draw maybe. But let's talk about what hydrogens would look like on this, because again, remember we have carbons here, 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 and then each of these carbons would have 2 hydrogens, right? And I don't know why I'm doing all of them, but I'm going to do all of them. Okay, so for this chair conformation, it's no different. This represents this. Again, remember, this chair conformation is representing this cyclohexane, just in a better way to represent which direction each attaching atom or functional group is going. So here's the best way that I've figured out how to do this, personally. You look for the points that are pointed up, and you draw a straight line up. You look for the points that are pointed down, and you draw a straight line down. Those are going to be hydrogens. All right, now for the fun part. These hydrogens, by the way, are called axial. Axial are going to be the straight up and down. So the ones that are straight up and down are called axial. Then we have our equatorial. Kind of like the idea that the equator is horizontal. So these are going to be a little more horizontal. For every one that I have up, I've got to have an equatorial going down, but it's not straight down, it's to the side down. So that would be for this one. So for all the ups, you're going to have one going down to the side. All the ups, you'll have one going down to the side like that. And then for all the downs, well, you'll have one going up to the side. And I strongly encourage you to do this several times. So really understand that that this is how we're going to do a conformation. Again, any of the points pointing down, you draw down. Any of the points pointing up, you point up. And then go do the equatorial ones Here, if I have an up, I must have a down to the side, equatorial. Let's do it for this one and see if we can practice. Okay, so if we have this conformation, and I want you to draw all the hydrogens around it, let's say it's just straight up cyclohexane. Again, you would, first for all the ups, draw straight up, and those would be hydrogen. For all the downs, you draw straight down. And now you can do the equatorials. If this one is up, it must have an equatorial down into the side. This one was up, it must have an equatorial down into the side. This one was up, it must have an equatorial down to the side. And now if it's down, it must have an equatorial up into the side. And this one here has an equatorial like that. So get used to it. These would be, if it were cyclohexane like this would be 50%, and this would be 50% conformation. So if you had a sample of cyclohexane, half of them would look like this, and the other half would look like that. Talks briefly about the boat conformation. That's a high energy conformation, and it's how these things flip. So if you have a chair form here, and it's in the easy way to draw one, it just essentially kind of follows through like what would happen. So first this part would come up, and then that part would come down, and you'd get this chair form. So it's kind of like an intermediate, the boat form. It's a very high energy. We rarely use it, but it is a good term to know when people are talking, whenever you hear the term boat form, you're talking about kind of that intermediate, was a chair, goes up and then forms a boat, and then this part comes down, you get the chair form. All right, so all axial become equatorial, and all equatorial become axial when you flip. We'll practice that. So let's look at this. Generally, you won't draw, like we just drew a ton of hydrogens. This is kind of messy. You won't usually draw that. You'll just draw what you're interested in looking at. So in this case, let's look at this guy. We're only looking at this carbon right here. It's got a methyl group here, and it's got a hydrogen here. Again, this point was pointing up, so on the up, we have a hydrogen. On this equatorial position, we have a methyl. If you were to flip that, remember that our one, which was up here, now comes down here when you flip it. And so this one's going to go down now, and when it goes down, the equatorial, which was pointed down, is still going to point down, but now it's straight down. Now it's become axial. And that's a beautiful thing about when you flip things, by the way. When you flip, what was down stays down. It's just going to flip from, but it's going to go from axial to equatorial, and vice versa. The same thing happens for when you have something up. If it was up, it's going to stay up. When you flip it, it's just going to go from axial to equatorial, or equatorial to axial. So let's go ahead and take a second to think about what would happen if we flipped these things. And then we'll figure out which one's also going to be the more stable. This is kind of important. Equatorial is more stable. So something's in the equatorial position, is less strain on the ring overall, and it's going to be the more stable structure. So you can see it's dramatically more stable. This CH3, when it's on the equatorial, forms about 95% of all of these compounds. So if you had a whole bunch of this compound, 95% would be this, and 5% would be just this one with the axial. Okay, so let's see if we can flip it. The fun part about this is mainly just drawing it. So let's look at this bromine. Here we have one in this conformation, so let's draw the other conformation. All right, and remember, what's up is staying up, what's down is staying down. So this carbon right here is now this carbon right here. This is pointed down, right? It was down equatorial, so that means it's going to be down axial now. So it was down equatorial, So that means it must be down. Axial in this one. All right, now let's look at this chlorine. Okay, so if you follow the carbons, this might not come as intuitively. When they're in the middle, it's a little harder to look at. But that was 1, 2, 3. We know this one's now 1, 2, 3. So we're looking at this carbon right here is what's going to have the chlorine. Remember, what's up stays up, what's down stays down, but just equatorial and axial flip. So here we had an up, axial, straight up and down. So that means over here it must be an up, equatorial. I hope that makes some sense. Okay, let's move on. Okay, we can represent cis and trans molecules pretty well here. So using this chair conformations. So if we have a cyclohexane, here we have trans. Remember, trans means different. So here you have this methyl group coming out toward you, and that methyl group going into the page, into the desk behind me. And here I have a cis meaning same. So that means I have one coming out toward me and another one coming out toward me. So the way we're going to draw this is if it's cis, they're both going to be up, or they're both going to be down. That's going to determine if it's cis or trans. So if they're both up or they're both down. But if it's trans, you'll have to have one up, one down. Okay, so let's go ahead and draw that. This asks for trans, but I think we might as well just do the cis as well while we're at it. So let's start with our conformation here. And we'll draw both axial and equatorial, because remember, if we have axial or equatorial, it doesn't matter if we flip it, there's still going to be one up and one down, no matter what you do. And I'll prove that to you here. Okay, so in this first one, they're methyl groups, so I'm going to go ahead and put it right here. We can put it anywhere, but I like using the 1. And maybe I should label these 1, 2, 3, and 4. So if this was 1, 2, 3, 4, this would be 1, 2, 3, 4. And that's why I went that way. You could also go 1, 2, 3, 4, but generally we'll just do clockwise. Okay, so 1, 2, 3, 4. I knew that this chair was pointed down, so I drew a straight line down. This one was pointed up, so I drew a straight line up. Right now, that is this trans 1, 3. Oh, I'm actually screwing up. I just drew 1, 4. I'll change it to 1, 4. Wasn't really thinking through it. Darn. Oh, I think that's because I was looking at this. That makes a lot more sense. Okay, sorry, this should probably say 1, 4. All right, I'll change that for the notes in class. Now let's go ahead and flip this sucker. And to flip it, we draw our other conformation, and we keep in mind that this was 1, so this is 2, 3, 4. Remember, what was up has to stay up. So it's still going to stay up, but now it's going to be an equatorial position up and to the side. And this one, number 4 over here, it was down, so it still has to stay down, but we're going to draw it down and to the side in its equatorial position. All right. If we had to decide which one of these is more stable, remember the equatorial is more stable. Because I guarantee you I'll ask something like that on the exam. All right, while we're at it, let's go ahead and do cis. 1, 4, dimethyl, cyclohexane. Just to make sure we understand this concept. So when I'm doing cis, they both have to be up or they both have to be down. So when we go to draw our conformation, if this is my 1, 2, 3, 4, let's do them both up for funsies. This would be CH3. And then my 4 would also have to be up. The only up on the 4 is the axial. Or excuse me, is the equatorial. All right, let's go ahead and flip that around. Draw my bad lightning bolt. This one is now this one. 1, 2, 3, and 4. Remember, what's up has to stay up. So this CH3 that's up is now going to be flipped into the equatorial up from the axial. And this CH3, which was equatorial and up, is now going to be axial and up. All right, so I hope that makes some sense. All right, now it says label each as cis or trans and draw the second chair conformation. All right, here I see this one pointed down, that one pointed down. That tells me this is cis. Here I see this one pointed up and this one pointed down. That tells me it is trans. So again, this OH was pointed down, this one's pointed down, so it's cis. This one's pointed down, this one's pointed up, so it's trans. Now let's go ahead and figure out the conformations. Oh, by the way, if I asked about stability in this one, one's equatorial, one's axial, one's equatorial, one's axial, you'd have 50% of each. There is no stable one here. They're both equally stable. All right, so let's go ahead and draw the cis one first. Okay, so if this was 1, 2, 3, 4, 5, 6, this is not for naming, this is for labeling the carbons on this thing. Just so you know, 2, 3, 4, 5, 6. So on my third carbon here, I had it down, OH. When we flipped it, it still has to be down, but it's going to be axial this time. And then my H, by the way, which was axial, now has to be equatorial. On the fifth carbon over here, remember this one goes up and that one goes in the middle, so my fifth carbon is actually right here. And that's why it's good to label them, I think. Helps you kind of remember what's what. So my fifth carbon over here, I got an OH, it's pointed down, equatorial. All right, that means it's going to be pointed down, axial on this one, and this one's going to be up, equatorial. Sometimes it's kind of hard to draw those, so I'm going to do a little better over here to show you something else you can do if they have a lot of what is going on. This is my problem. That's what I needed. I need the sound effects. That's how to do it. Okay, sometimes these are kind of like hard to draw, and if you want to put an OH down, you can actually even do a dash line into an OH to represent that this one was going down behind there. So, and sometimes you'll have a whole bunch of stuff over here. Like in this case, we also have an OH here, and that can look kind of messy, right? Because we had this hydrogen over here and this hydrogen up here. So you can draw a dashed line to represent this OH way back behind there. That might be helpful as well. All right, now let's look at the trans one. Again, we knew it was trans because we had one going down and one going up. If this is our carbon 1, this must be our carbon 2. So let's draw the flip. Our carbon 1 is now down here. Our carbon 2 is here. Here we had a chlorine that was equatorial down. That means here it must be axial down. Here we had a chlorine that was equatorial up. Here it must be axial up. And that would be the flip conformation. If I asked you to tell me which one is more stable, right here they're both axial, here they're equatorial, so this one is more stable. Stabler. Let's just write more stable. And over here, these are equatorial. This is also more stable. All All right, cool beans. Let's see how we're doing. Oh, even more. They just keep coming. Okay, so draw the two chair conformations for this thing right here. First helps to label it. I'm just gonna start right here because that's how I would name it probably. 1, 2, 3, 4, 5, 6. So just a fun name, right? This would be 3,4 dimethyl, and then a 1, or actually 1 ethyl, 3,4 dimethyl cyclohexane, because the ethyl comes first alphabetically. All right, so let's go ahead and draw it. We're gonna take first our boat, or our chair conformation, excuse me. All right, some things to think about. This ethyl group and this methyl group are going to be cis. So you can make them both up or down, whatever you want. I'm gonna make them both up. So right away, I know it's pointed up, I can draw a straight line up. So I'm gonna put my CH2, CH3 going up right there. And on my fourth, 1, 2, 3, 4, I also have an up methyl. So I know that there's an axial going down. That means my methyl must be up equatorial. And then on the second carbon here, right here, I must point something down. And that's kind of helpful because it's already, like, I don't know, this comes intuitively to me like it's pointing down, so just draw down. All right, let's go ahead and flip that ring and see if we can find something more stable. So here we have a horribly drawn lightning bolt. If this was 1, 2, 3, 4, now this is 1, 2, 3, 4. What's up stays up, what's down goes down. We just flip axial and equatorial. So this CH2, CH3 was up. So in order for it to stay up here, it has to be equatorial. This CH3 was down. It must remain down. It's going to be equatorial as well. And this CH3, which was equatorial, is now going to be axial. Okay, and finding out the most stable conformation, I have one thing that's axial and there are two things over here that are axial and one equatorial. Over here I have 2 equatorial and 1 axial. This is more stable. All right, let's see where we're at now. Ooh, oxidation reduction. Anyway, so practice those chair conformations. It definitely takes some practice. As you can see, I still can't draw the one conformation very well. I don't know why. Maybe you guys can give me some tips. But let's look at oxidation and reduction briefly. I don't want to spend a lot of time here. This is a lot from Gen Chem. Usually we look at oxidation numbers and determine if oxidation number went up or oxidation went down. That tells you if it was oxidized or reduced. But here, a more simplistic way of looking at it is the following. If you increase the number of carbon-oxygen bonds, it was oxidized. If you increase the number of carbon-hydrogen bonds, it was reduced. Let's put that into action and see if we can make some sense here. All right, so carbon-oxygen. So if we make carbon-oxygen, it is oxidized. Oxidized. And if we make carbon-hydrogen, it's going to be reduced. Let me explain what I mean by that. So here we have ethanol. It's got an oxygen to a hydrogen, and we formed this new thing. It's got this bond to oxygen and hydrogen and an oxygen-hydrogen. I hope you agreed we added more carbon-oxygen bonds. Therefore, this was oxidized. There are more CO bonds now. We look at this one. I'm going to draw out the hydrogens just to prove my point here. Here we would have a hydrogen there, right? And we would have a hydrogen there. And then over here, when you take away the double bond, when you're a single bond, don't forget each carbon needs 4 bonds, so this would have 2 hydrogens on each one. So we went from a carbon hydrogen here to a carbon hydrogen and a carbon hydrogen, so 2 carbon hydrogens, so 1 to 2. Therefore, we increased the carbon hydrogen bonds, and this was reduced. More CH bonds. All right. Hope that makes some sense. Ooh, we're flying through this sucker. All right, combustion. All right, this is, if you've had me in Gen Chem, you know this is one of my favorite things to do, is talk about combustion reactions. But unfortunately, in OChem, we're not going to get as far into it as I want to. The main thing with combustion reactions is that you take some kind of carbon hydrogen containing compound. There could even be oxygen in there, but we're talking specifically alkanes, so let's just say a bunch of carbon hydrogens. You react it in the presence of oxygen. You light it on fire, you give it enough energy to overcome its activation energy, and you get CO2 and water, right? The main thing that I want you to be able to do is to be able to balance these reactions. I'll post a separate video of balancing the reactions, but know how to balance. In fact, screw the separate video, I'll just do it right now real quick, just to make sure we're on the same page. So when you're balancing combustion reactions, let's start with this first one. So we've got CH4 plus O2. Even though we already know these coefficients, let's pretend we don't, because this will be a question, most likely. So if I said balance this, one of the best ways to balance a combustion reaction that I've found is to just CHO it up. CHO. So you find the number of carbons on the left, find the number of carbons on the right, you make a match. Move on to hydrogens, you do the same thing. You move on to oxygens, you do the same thing. So for example, on my left over here, I have 1 carbon. On my right over here, I have 1 carbon. They're already good, so I don't need to do a thing. Let's do hydrogen. On my left over here, I have 4. On my right over here, I have 2. I always take the big number divided by the small number, and that's the coefficient I put there. So 4 divided by 2 is 2, so I'd put a 2 there. And now that gives me 4 total hydrogens over here because I have 2 of the H2. Then I move on to oxygen. On my left-hand side over here, I have 2. On my right-hand side, make sure you add up both of these. I have 2 from the CO2 and 2 from the H2O for a total of 4. 4 divided by 2 is 2, so I put a 2 there, and that is now balanced. So let's move on to the other one real quick. So here we had isooctane. Here's the beautiful thing about knowing what the formula would be for something, like if you go up and you count all the carbons in here, I got 1, 2, 3, 4, 5, 6, 7, 8 total carbons. Okay, so you have 8 carbons in there. To find out the formula, it's Cn times the H times 2n plus 2. So this is how we can always figure out for alkanes. And there's even formulas for alkenes and alkynes, which we'll learn as we proceed. But for 8, this tells me that I have 8 carbons. My H is going to be 2 times 8 plus 2. 2 times 8 plus 2 is 18. So C8, H18. So I want to be at the point where I can say, I can maybe just give you this structure and say, tell me the combustion, give you this structure and say, tell me the combustion reaction of it, or balance the combustion reaction of it. So we know that it's C8H18. Again, you could have counted all the hydrogens, but it's way faster to just notice it's an alkane, know that there's 8 carbons, and then say 8 times 2 plus 2 tells me the number of hydrogens. All right, with that being done, remember we're going to react it in a combustion with O2 to form CO2 and H2O. Now this is actually one of the compounds in gasoline. It's what helps drive your car forward, is this combustion reaction right here. All right, so let's go ahead and balance it. Remember, we're balancing a combustion, so we CHO it up. On my left-hand side, I have 8 carbons. On my right, I only have 1. 8 divided by 1 is 8, so I put the 8 there. Now I have 8. I move on to hydrogens. On my left, I have 18. On my right, I only have 2. 18 divided by 2 is 9. So I put a 9 there. And now I can move on to my oxygens. On my left, I have 2. On my right, I have 8 times 2 is 16, plus 9, for a total of 25. 25 divided by 2 is 12.5. Don't freak out. It's okay to do a 0.5, but because we can't draw half molecules, this would work really well in Gen Chem too, but because we can't draw half molecules, what we're going to do is have to divide, or have to multiply each of these by 2 to get rid of this 0.5. So the whole thing times 2 gives me 2C8H18 plus 25O2, yielding 16CO2 plus 18H2O. And that's how we would balance combustion reactions. So if I ask you to balance a combustion reaction and I give you a molecule, that's kind of what I expect you to do. Combustion reaction. All right, so sorry for those of you who had to fast forward through that. If you had me for Gen Chem, you were very prepared for that. All right, last but not least, let's talk about lipids. Lipids are, they're biomolecules and they're really good at storing energy. In fact, I think they're the best energy storage molecules, biomolecules there are. The weird thing about these is they're defined by physical properties. Not some kind of functional group. So the physical properties are that they're going to be soluble in nonpolar solvents and insoluble in water. And also that, again, they're biomolecules, meaning they're created in biology. For example, cholesterol is a good example of one. It's just got this little OH group right here, but then a ton of this other nonpolar stuff. So this would not at all be soluble in water because it's got, remember, the more than 5 carbons after that OH group. Okay, over here, this is prostaglandin. It's prostaglandin. It's kind of an important molecule in regulating like inflammation and stuff. And I think like for non-steroidal anti-inflammatories like ibuprofen, what ibuprofen does is it downregulates this. It says no and tries to get rid of it. And that's how ibuprofen works. Beeswax. So you can see that these things look all very different, right? But they have one thing in common, and that's they got some kind of polar business going on, and then a whole bunch of other stuff, whole bunch of non-polar stuff. And so those are lipids. We're not talking too much about them other than that. And they're good energy storers. Why they threw them in here is mainly just because they have a lot of alkane activity on them, and that's how they ended up in this chapter. And I'm sure we'll talk about them at some point later on. If not, you'll definitely get into them in Gen Chem 2, or in OChem 2. So, all right, y'all. Hope that helps. Have a great one, and I will see you in class later.